Hi, everybody. Can you hear me? I don't know. Hi, everybody. I wanted to run through one of these tougher energy and momentum combination problems with you. It's number 33, the last one on that sheet I gave you. And I want to just try to identify a little bit of a strategy for you. And one of those strategies is to make sure you draw yourself a little picture. All right, so I'm going to start with a bullet. We'll call this object 1. Here's a block. Call that object 2. All right, what happens is the bullet hits the block, and then now the block is on a horizontal surface. Let me identify that surface here. Still 1 and 2. Right, the bullet, it says, becomes embedded in the block. And afterwards, these things move this away. And then later, there's kind of a, this is like in the beginning and later and even later. So even later, this thing squishes up into a spring. Well, the block doesn't smush, does it? But the block moves over here and compresses this spring. All right, so what you sort of have to do here is you got to figure out, first of all, do I use momentum? Do I use energy? How do you know? All right, well, here's the big deal. If it's a two-body interaction, right, and that literally means one object exerting a force on another, coming into contact with another. Well, then that's momentum. So that's this part. So here's our initial, and here's our final. Now notice, that only captures 2 of the instants that we've talked about, because then we have this part. And in this part, or range of time, we actually have this as an initial, and this is a final. Right? And what we can try to do sometimes is identify this that's the overlap. All right, now let me back up a step, because if we look at this second part, the part in blue, what we say is, well, this is no longer a two-body interaction. It's not 2 objects that are still exerting forces on each other. This is a case where we trade velocity. Let me see. Ungroup. It's never going to let me do it, is it? Is it? Yeah, that's it. Group. Right, we trade the velocity of this thing for compression of a spring over here. So we trade one kind of energy for another kind. All right, so I don't know. If we go for motion to height, whoops, do this in blue anyways. If we go forget about motion. If we trade speed for height, or height for speed, or speed for compression, or any of those sorts of transitions between one kind of energy and another, well, then we go conservation of mechanical energy. All right, so here we trade the speed of this object for the compression of that spring. And even though it's the bullet and the block together, we can just sort of say that this is a single object. Fair enough? All right, now the overlap part. The overlap part. The thing here is that, well, notice, we're calling it both a final and an initial. So what we're going to have to say here is that the final from the red part becomes, check this color coding out, becomes the initial for the blue part. That's the hard, I mean, that's a hard part. Now, in this question, it doesn't move forward in time. All right, they actually tell you something about how far the spring is compressed. So that means you know something about this final, right? You really know something about that, which means you can back up and find out what the initial mechanical energy was, which is going to tell you the initial velocity of that block. Well, the initial velocity of the block in the energy conservation part is actually the final velocity of the block and the bullet during the interaction part, during the two-body interaction part, during the momentum part. All right? So I'm going to run through this whole solution right now, using kind of exactly what we see here. So the things we know, I'm going to say that, well, if we say for our conservation of energy part, GPE initial plus KE initial plus EPE initial, GPE final, KE final, sorry, plus EPE final. Well, in the beginning of our blue part here, those can both go. They're both at the same height. We'll call it 0. The block comes to a stop. In the beginning of the blue part, the spring is not compressed yet. So we can say 1/2 mv initial squared equals 1/2 kx final squared. They tell us k, 150 newtons per meter. They tell us x, 0.8 meters, be careful. They tell us the mass of the two objects together. That's one thing, right? M here is m total, right? K is 150 newtons per meter. X, 0.8 meters. We need it in meters. Get rid of these 1/2s. So we can find V initial. Again, M total. So, calculator. Kx squared 150 times 0.8 squared divided by the total mass. Again, it has to be in kilograms, so 0.112. Oh. Yeah. Get out of town. Yeah, it helps to take the square root. Oh, no, don't do it. Don't do it. 857. Square root 857. 29.3. All right, so the initial 29.3 meters per second. Now, what speed was that? Well, that's this speed right here. But notice, like we said, oops, I'd like this to be in green. That speed, the beginning speed of the energy conservation part, is the final speed of our two-body interaction part, this part up here. So now we know how fast both objects end up moving after they've collided inelastically. So I'm going to now say that m1v1 initial plus m2v2 initial is m1v1 final plus m2v2 final. Now, initially, and now when I say initially, I mean initially here in our two-body interaction part. The second block isn't moving. And here's what else I'll say. M1v1 initial is, well, M1 plus M2 V final, because they move together. This is an inelastic collision. They have a common final velocity after the collision. So if we want to know the initial velocity of the bullet, or again, what's our VF? Our VF, how do I want to do this? Our VF is really that VI. Same thing, right? This VI here, the initial velocity when it started moving this way, is the same as the final velocity after these two things collide. So that's why we found this first. And that goes in there. All right, so we do that answer times 0.112 divided by 0.012. 273. There it is. Okay, so I think that, what I'm trying to get at here is if you can, first of all, draw yourself a picture, right? And see if you can identify the two different physics phenomena that we can analyze, right? Figure out which one is a momentum part, which one's an energy part. Figure out where the overlap is, and based on that, figure out which two variables are actually the same exact value. Okay? If we had one, we talked about one like this, the ballistic pendulum one, right? Where, let me do this, sorry. Where, let's take this one. Bullet moving this way, pendulum like that, right? These guys over here. And let's see. And then later, let's see, this thing, let's say the bullet goes through, like in that one example we had. Well, this thing's now moving that way, right? And then it ends up swinging up to here. Right? So what we can look at is, what are the two physics phenomena? Well, here is a conservation of momentum thing. Two-body interaction. Here, you saw me draw the same diagram in class. Here is a conservation of energy thing. So this is ME initial is ME final. This is net initial momentum equals net final. And where's the overlap? Well, the overlap is right here. Where, let's see, the initial velocity for the energy conservation part is the same as the final velocity of the, oh, sorry, should probably call that 2, right? If we're calling this object 1 and object 2, here's object 2, we would call that V2 final. All right? What other examples can we talk about? There's one also in your notes where we have this. Not in your notes, but in that homework problem. Here's a baseball. Here's a bullet that's shot vertically into the baseball. I think what happens next is the bullet embeds itself in the baseball, and then they end up here at max height, right? So now we have a two-body interaction. We have an energy conservation, and we have the overlap. That's object 1 and that's object 2. Well, it looks like the final velocity, and notice I'm not writing 1 or 2 because it's an inelastic collision and they stick together and have the same common final velocity. Their final velocity becomes the initial velocity in that energy conservation part. All right? Well, okay, we had another one like this in the notes. Just, you know, nothing wrong with talking about it again. We had a block here. That's right. We had a block here, 1 and 2. Move this guy over a little bit. Sure, fine. Well, what happens? Block 1 starts up there and ends up down here, moving at a speed like this. These two things end up stuck together, moving like that. And then some other stuff happens. We had to turn this thing into a horizontally launched projectile. But forget about that for now, because right here, we have a single object trading height for speed. ME initial is ME final. Then we have a two-body interaction. And that's, well, net initial momentum equals net final. And here is our overlap. So the final velocity of the object in the energy conservation part becomes the initial velocity of what we can probably appropriately call object 1. Oh yeah, we did. Look, there's 1 and 2. Yeah, 1 and 2. Okay? So how many ways are there to ask these questions? I don't know, there's a lot. But I think, like I said, if it's a single object, trading height for speed, or speed for height, or spring compression for height, or spring compression for speed, a single object, that's an energy conservation. If it's one thing interacting with another thing, two objects, that's a momentum conservation. Find the place where, find what we call the overlap, and what final equals what initial. All right, folks. I don't know if it helps. I hope it does. Draw diagrams. Diagram good. See you bye. See you bye. Okay, bye.